Hello, 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 hello. So, hi everyone. My name is Dilshad and I am here to discuss today's Codeforces contest. So, yeah, so let's start. So, this is Codeforces Round 1077. Yeah. So, let's start with the first question. So, let's read the first question. So, we are given an integer n and we have to construct a permutation p for which this condition is satisfied. Okay. Pi minus pi plus 1 is divisible by I. Okay, so for every I from 1 to n minus 1, this condition has to be satisfied, right? And they have given that there always exists such a permutation. So, so we just have to print that permutation. Okay, yeah. So what are we given? So we are given an integer n. Okay, and for which we have to output a permutation which satisfies this condition that pi minus pi plus 1 is divisible by I. Okay, so and for all I less than or equals to n minus 1. Okay, right? So you would notice, so this is basically the difference of the adjacent elements, right? So you would notice that the maximum value of I is n minus 1, right? So for p of n minus 1 minus p of n, uh, this difference is equals to what? This difference has to be equals to n minus 1, right? Because the maximum difference between any two element in a permutation can be n minus 1, and for the difference to be a multiple of n minus 1, this has to be equals to exactly n minus 1, right? So from that we can conclude that one of these two elements has to be 1 and the other elements has to be n, right? So if we start constructing our permutation from the end, let's say we make let's say our last element is n, then second last element is automatically 1, right? So then this difference is divisible by what? N minus 1. Okay. So, and to make and to make this difference uh, a multiple of n minus 2, there's only one way to do is like by putting n minus 1 here, right? And similarly, there's only one way to make this difference divisible by n minus 3, which is what? Which is by putting 2 over here, right? So from this we can see that for such a permutation to exist, we have to construct in this way. So if I put n here, then I have to put 1 after that, and then n minus 1, and then 2, and then n minus 2, and then 3, and then n minus 4, and then 4, and so on, right? N minus 3, right? So, yeah, there's only one way to do this, right? So, what I'm gonna do is I'll start constructing my permutation from the back, and yeah, and then I'll just print the numbers in this order. Okay, so let's move into the implementation. Let's look into the code to get a more clarity. Clarity. So here's the code. So I have taken a two pointer, which is my left boundary and the right boundary. Okay, so this is just useful um, to know till what values I have used till now. Okay, so I am starting from back, and uh, to get an alternating kind of pattern, I'm just using the parity of the index. That's all. So if the parity of the index is odd, then I'm using my right boundary, that is R, and then decrementing R. Otherwise, I'm using L and then incrementing L. And in the end, I'm just printing my whole array. Okay. So this print is nothing but just this. Okay. So that's all for the first question. So the overall time complexity. So the overall time complexity is what? It's just big O of n, and space complexity is what? It also is just big O of n. Okay. So let's move into the next question. So let's read this question. So we are given a binary string S, which indicates a row of seat. Okay, and the ith seat has been occupied by a student if Si is equals to 0. Sorry, the ith seat has been occupied if Si is equals to 1. Otherwise, Si is equals to 0. That basically indicates that the seat is free. Okay, and it is guaranteed that no two adjacent seats are occupied, right? And throughout this question, and like throughout this process, we also have to maintain this pattern that no two adjacent seats have to be occupied, right? And what do we have to do? We have to add more students until it is impossible to sit anyone else in the row. Okay, yeah. And we have to calculate the minimum number of students that needs to be seated so that it is impossible to add any more student into this row. So this basically means that whatever the vacant spaces are there, we have to fill that in such a way that there should not exist uh, any any two like spaces in which the students are seated, right? Like no student should be adjacent to each other, and we also have to ensure that there is there is no possibility of adding any more student. Okay, and out of all those ways of doing this, we have to find the one which minimizes this. Okay, and we just have to tell the minimum number of students that can be seated in this particular row. Okay, and the constraints are the usual linear constraints that n is less than or equals to 2e5, right? So let's start by some examples like what if the string contains all the zeros? Okay, so what if the string contains all zeros? Something like this. Then what is the best way to fill this? Can I start filling by the first index? So if I put a student here, is this the optimal way of doing? Like it is not. Why? Because we can always if this one we can start with the second one, right? So this is not optimal. So what I can do is I will keep this empty, and then I will put one student over here. Then I can obviously leave this one as well, right? Can I leave this as well? I can leave this one as well uh, if there is at least one in the left. Okay, so if there is one, then I can put a zero over here. Okay, and I can put another zero over here, right? So what we can observe is Let's say my string starts with 1, then I can, how many maximum zeros that I can put? I can put 1 0, I can put in another 0, but I can't put a third 0 because if I put a third 0, then this 0 has to be converted to 1, right? Which is not optimal. So, followed by 1, I can at most put two zeros, okay? Right? And after these two zeros, I also need to put one because if I'm not putting a one, so if there is a one and then it is followed by two zeros, but then the string ends. Okay. So if the string ends with two zeros, then what does it mean? That it means that it is still not complete. Like a one has to be placed over here, okay, to satisfy the condition, right? So as long as, so let's say there are some number of vacant spaces, uh, and in the left hand there's a one, and in the right hand as well there's a one. Then among all these positions, what we can do is we can leave two zeros, like we can fill two zeros over here. Then we have to fill a one. Then again we can leave two zeros, right? So there are there are three kinds of spaces. Okay, so the first kind of spaces, the spaces in which uh, in both the left boundary and the right boundary there's a one. Okay, the second kind of spaces in which only one end contains a one. Okay, so let's say there's a 0 0 0 and then here's a one. Okay, so in this case only one end contains a uh, occupied state. Okay, the third case is that there is no one in both the ends. Okay, so this is basically all are just zeros. Okay, so what we are going to do is uh, we'll try to we'll try to find an optimal strategy to fill the ones in all of these three cases. Okay, so in this particular case, let's say the number of zeros is x over here. Okay, so for case one, so for case one, so for case one, x number of zeros are there. If x number of zeros are there, x number of zeros are there, then what we can do is we can do something like, okay, so if x number of zeros are then what we can do is, um, so since it is case number one, then like in both the ends they are bounded by a one. Okay, so we can leave these two spaces with zeros. We can leave these two spaces as zeros. Okay, but then we'll have to fill one and so on. So we can arrive at a formula. So the formula is uh, so let's try to figure out what the formula can be. Okay, so let's say that x is equals to 1. Then how many ones I can put? I don't have to put a 1 over here, so the answer is 0. If let's say that x is equals to 2, then again I don't have to put anything, the answer is again equals to 2. Let's say that x is equals to 3, so I'll have to put 1. Let's say x is equals to 4, then again I only need to put 1. Let's say x is equals to 5, so 5 means what, like there's a 1 and then there are 5 zeros. Okay, so I can leave these two zeros as it is and then I can make this one a 1. Okay, right, and in that way my condition will be satisfied, right? So for x is equals to 5 as well, I just need to put 1. What about x is equals to 6? So for x is equals to 6, I would need to put 2, right? because if I'll add another 0 over here, then I can't satisfy the condition with just one, okay, with just one student, okay. So for x is equals to 6, answer is going to be 2. So you can see that there is a periodicity in 3, okay. There's a periodicity in 3, and for x is equals to 3, it is 1. So my formula can be directly x by 3. My formula can directly be what? It can be x by 3. Okay. Yeah, right. So for case is equals to 1, my formula is just x by 3. Okay. These many extra ones I am going to required. What about case is equals to 2? So for case 2, there's a 1 in the end, and then there are all zeros. Okay. So again, let's try to get a formula for every x. Like let's try to, yeah. So for x is equals to 1, my answer is obviously 0. For x is equals to 2, my answer is going to be 1. Why? Because there's a two zeros and then there's a 1. So this 0 has to be made equals to 1, right? So for x is equals to 2, I'll have to add one student. For x is equals to 3, uh, again 1. For x is equals to 4, again 1. For x is equals to 5, I'll need 2. Why? Because let's say there's a 1, and then there are 5 zeros, right? So for this one, so for this 0 over here, if I make it 1, then again there are two spaces, right? And for this 0, I'll have to make it equals to 1, okay? So then we need two ones, right? So for the case number 2, the formula I'm getting is what? The formula I'm getting is x plus 1 by 3, okay? Similarly, if you would do for case 3, you would get the formula what? You would get the formula x plus 2 by 3. Okay. So combining these three results, we can write the whole code. Okay. So what we have to do? We just have to do this. Do what? So in the whole string, I have to identify the substrings which contains all the zeros. Okay, like contiguous substring which contains only zeros. So whatever those sizes is, let's say x1, x2, x3, right? And I'll also have to identify that if there exists a 1 in its left hand and if there exists a 1 in its right hand. Similarly for this substring and for this substring, okay. So by identifying if there exists a 1 in the left hand and right hand, uh, we can comment on its type. Okay, is it of the case 1 or is it case 2 or is it case 3? So whatever the case is, we just have to apply the formula. Okay, so let's look into the code for once. Yeah, so as you can see, for C is equals to 0, C is equals to 0 denotes what? That the whole string contains only the zeros. That is basically what? That is basically my case number 3. So I have just handled case number 3 like separately. Okay. So for that I am just outputting n plus 2 is equals to 3, right? And then I am traversing through the array, through the string, and then I am trying to find what? I am trying to find contiguous substrings of all the zeros. Okay. So in this way, I am trying to find what? How many number of zeros are there? Okay. In this continuous segment. So if I is equals to 0 or j is equals to n minus 1, this denotes what? This denotes that it is of case 2. So when it is of case 2, I am adding this thing in my answer. Otherwise, I am adding just x by 3. And I am initializing my answer with what? I am initializing my answer with c. C denotes what? C denotes my initial number of ones in the string. Okay. So that's that for this question. Let's discuss the time complexity. So the time complexity is just big of n, and the space is also what? Big of n. Okay. Yeah. So let's read the third question. So we are given an array of length n, and for an integer k, we call the array piggy if and only if it is possible to sort a in non-descending order. That is what? That is, we just have to sort the array. Okay. By performing the following operation any number of times. Okay. So first select two indices I and j such that ai minus aj is greater than or equals to k. This means what? We can swap any two numbers in the array as long as their absolute difference is greater than or equals to k. Okay. Yeah. And then we have to determine the largest such k for which this is possible. If such an integer doesn't exist, then we just have to output -1. Okay. And the constraints are like nominal. N is 25. Okay. So, uh, so k is equals to -1 when it is going to happen. Okay. So it doesn't matter how the array is. We can always swap like any if even if k is equals to 0, there's always a way to swap these numbers, right? In case of what? In case of k is equals to 0, we can swap any two numbers if k is equals to 0, right? So this basically means that k is equals to -1 is going to happen when the array is already sorted. So if the array is already sorted, that basically means what? We can choose any k because we don't really need to do any operation, so we can choose any k. So if the array is already sorted, then my answer is going to be k is equals to -1, right? So that is the edge case. Okay. So what if my array is not initially sorted? So if the array is not initially sorted, let's say my this is my original array, right? A1, A2, AN, and let's say B denotes my sorted array. So if I sort this array A, then this denotes what? This denotes my B. B1, B2, B3 until what? Until Bn. Okay, right? So obviously this array A is not equals to B, because if they were equal, then that would be the case of what? K is equals to -1. So there exists at least some index j. So there exists some index j for which such that A of j not equals to B of j. Okay. So there is exists at least some j. Okay. So yeah, so let's focus on that particular index. Okay, so we are focusing on the index j for which this condition is true. That is, aj is not equals to bj, which means that the correct position of this value aj is actually not j. It is something else. Okay, yeah. So that basically means that I'll have to swap this value. Okay, I'll have to swap this value somehow, and then after some number of swaps, I'll have to place this value to its correct position, whatever its true position would be, right? So, and to do swaps, and to do swaps, I can do so let's say for this particular AJ, let's say what I'm saying is I'm saying like there are some number of numbers, okay, x1, x2, x3. So if I say that like AJ can be swapped with any of these values, x1, x2, x3, then which value I'm going to choose? So optimally it makes sense. I would choose such a value of x whose AJ with xk is like maximum, okay, right? I will use such a value, right? So the absolute difference between AJ and so the absolute difference between what? AJ and XK has to be maximized. So this value AJ and whatever value I am swapping it with, let's say X, has to be maximized, right? Is maximum. So for any value AJ, uh, with what numbers its absolute difference is going to be maximum. So this is going to be maximum with either one of the two numbers, okay? Either with the minimum number, either with the minimum of the whole array, okay? Or what? Or maximum of the whole array, right? Right, so I can swap this value with any of these values, right? Either with this or this. So for this, so if I do a procedure like this, if I do a procedure like this, so let's say there are two numbers, AI and AJ. Okay, and let's say my minimum is something. So let's say my minimum is X and my maximum is Y. Okay, yeah, right. And for AI, my maximum difference is with what? Y. And for AJ, my maximum difference is with what? X. Right. Or it can be also like for both AI and AJ, my maximum difference is with Y, and for both AI and AJ, my maximum difference is with. But let's just consider this case first. Okay. So if AI's maximum difference is with the maximum element and AJ's maximum difference is with the smallest element. Okay. So in that case, how can we and let's say we want to swap this I and jth element. So how are we going to swap it? Okay. So to swap AI with AJ, I am going to only use like if I am ever involving AI in a swap, then I am going to swap it with Y. And if I am ever involving AJ in a swap, then I am only going to use it with what? With X. Okay. So I can do something like this. I can first swap AI with Y, and I can swap AJ with X, and then I can swap, XY. Yeah, and then I can swap XY. So after this, what is going to happen is Y is in the place of AI and X is in the place of AJ, like after this swapping operation. So then I would do these two swaps again. So then what is going to happen is, so this whole thing gets transformed into what? So this whole thing gets transformed into AJ is here, AI is here. Okay. Yeah. And then X is here and then Y is here. Yeah. Yeah. So this is going to be like this, X and Y. Yeah. My initial goal was how can I swap AI and AJ? And then I have been able to do it with this. Okay. And I have already proved that the optimal way to involve AI with any swap is to just swap it with this either with the minimum or the maximum, uh, whosoever with the maximum is. Okay. So, so what I can do is, so for all the numbers, so for all AI for which AI is not equals to BI, I'm going to do what? I'm going to take the minimum of maximum of. So my answer is going to be what? The minimum of maximum of what? Like absolute of AI minus minimum, comma, absolute of AI minus maximum. Okay, and that's all. So let's look into the code for to get a more clarity. So as I said, B is just my sorted array. So if they are, so if my original array is already sorted, then I'm just going to print -1. Otherwise, I am just so if they are not in the right position, then I'm going to do what? Then I'm just checking its distance with the minimum and its distance with the maximum. So I'll take the maximum of it. So the maximum of the those two and minimum among like for all these indices, I'm going to take the minimum of this value, okay? And then I'm just printing my answer, okay? So yeah, that. Let's discuss the time complexity of this question approach. So time complexity is uh, so since I use set, so it is n log n. But even if you won't use set, you can do this. So in that case, it is going to be big O of n. And what is my space complexity? My space complexity is just big O of n. Okay. So let's move on to the next question. So let's read this question. We are given two non-negative integers x and y, and we have to find two integers p and q such that their bitwise AND is 0, and the sum of their Manhattan distance or just their absolute differences is minimized. Okay, and there are 24 test cases, and x and y is less than 2 to the power 30. Okay, so we are given some x and y. We have to transform this x into q. We have to transform this x into q. Right, such that the AND of P and Q is exactly equals to 0, and the summation of x minus P plus y minus Q is minimized, right? Right? So, what would be the best way to do it? Okay, so let's start from the highest bits. Okay, so let's say I'm at the 2 to the power 30 or like the 38th bit. Okay, so 38th bit. Like again, x is less than 2 to the power 30, so I'm just saying. So I am starting with the largest bit. Okay, so let's say I am at some ith bit, and in both x and y, either in either like let's say in both x and y it is 0. Okay, let's say in x it is 1 and in y is 0. Let's say in x is 0 and y is 1, and x is 1 and y is 1. Okay, so in this case we don't have to do anything. In this case as well we don't have to do anything. In this case as well we don't have to do anything. And for this case only, we have to fix. Okay, we'll have to do something because and is going to be non-zero. Okay, so my number is like this. Let's say this is x, this is y. We are at some index. here, let's say, right? And here both are 1. Okay, and you can notice that I can either increase x, I can increase x, x can be increased, x can be increased or decreased. Like we can do both. X can be increased and decreased. We can do both of them, right? So at some index, uh, if at some index my bit is set in both x and y, okay, then what I can do? So I'll consider the case when I have to increase something. Okay, uh, yeah, like if I'm increasing, I can do one thing. If I'm decreasing, let's say if I'm decreasing, so what I can do is I can make this 0, and then what I can do is I can make all of this 0, right? I can make all of this 0. And more better way to do is what? Like let's say there is a 1, there is a 0, there is a 1. Okay. So then what I can do is, so I'm making a 0 over here. I can make a 0 here as well. I can make a 1 here as well. I can make a 0 over here as well, right? So in this way, so if I'm decreasing, so this can be my optimal way of decreasing numbers. Okay. What if I'm increasing? So what if I am increasing? Okay. So what if I am increasing? So even if you would, let's say this is the first index where my bitwise end is non-zero. Okay. So if there exists another index, if there exists another index j which is greater than I, for which my bitwise end is non-zero, then I would want to fix from that index only. Okay, I won't really care about this index. So if I if I fix from that index, then I don't really have to care about the subsequent indexes. Okay, so if I'm decreasing, I just have to care about the first index where my bitwise end is 1. And let's say my bitwise end here is 1, then what I'm going to do is, so I'm just going to so for all the subsequent bits I'm going to make it as 0 if the other bit is set, or I'm going to make it as 1 if the other bit is not set. Okay, so that is the case when I am decreasing. What about increasing? And what is going to be my maximum sum of the differences here? So the maximum sum of the differences over here, you can notice that it is going to be less than or equals to 2 power I. That is for sure. Like it is going to be less than or equals to 2 power I. Okay. So we now know for sure that my maximum upper bound on the answer is 2 power I. Okay. So when would I want to increase a number? When would I want to increase a number and then make the bitwise and equals to 0? So when would I want to increase either x or y? Right. So again, let's start from the highest bit and move on to the smaller bits. Right. So let's say this is the first index in which my bits are set. So this is the first index where my bitwise end is non-zero, right? So what I would want to do is I would want to make it 0 somehow. Somehow I would want to what? I would want to do what? I would want to make it 0, right? So if I am making it 0 by adding something, so the best way to add is what? So the best way to add is, so if you would consider this number only, or just this number only, right? So if you would consider this number only, so whatever its value is, 2 की power I minus whatever its value is. Okay, so whatever this value over here is, 2 की power I minus value, this is the most optimal way to add something, so that this whole part is going to be what? It is going to be 0, right? So let's say I have made this 0 by adding something. So if I'm adding something, then it is going to do what? It is going to it is going to carry some bit forward. So, like initially there was a 1, and I am again adding a set bit. So, this is going to be 0, but after it, it is going to carry some 1. So, let's say here also it was initially 1. So, again it is going to carry. So, it will keep on carrying until what? Until two things happen. Either, so what are those two things? So, obviously, in the second number, it is going to be 0, and in the first number, it can either be 0 or it can be 1, right? So let's analyze these two cases independently. So initially, if there was a 0, let me write it again. So yeah, let's say there was a 1, there was a 1, here was a 0, here was a 0. Let's say there's a 0, there's a 1, there's a 1, there's a 0. Okay. So if I'm right, so it will keep on carrying until it reaches this index. So in this index, again it is going to be 1, and these all have become 0. Okay. So it is going to carry something, right? So when it is going to carry something, what is the best way to add? So over here, I'll again have to add here, or I'll have to add here, right? But you would notice when I'm going to add for the second time when I am adding, the cost is definitely going to be greater than 2 ki power I, right? So whenever there is a comes a case that I am adding something greater than 2 ki power I, then it makes no sense, right? Because we have just figured out that the maximum upper bound can be 2 ki power I. So if my required cost is greater than 2 ki power I, then I am not going to add anything, right? So we have come to a conclusion that whenever I am adding something, I just have to add one set bit. So I am going to add just one set bit, and then I am going to check what's my required cost. So whatever my cost is. Okay. So how I implemented this is I I did I did it for every bit. Okay. So for every bit I am adding 2 ki power I, and then I am checking uh, what is my required cost X. Okay. And what is, and also that if P and Q is equals to 0 or not. Okay, so if this is 0, then I am going to update my answer if this required cost is the least till now. Okay, yeah, and otherwise the other way to do is just decrease the numbers. Okay, so let's look into the implementation for once. So this is my pair answer, which denotes what? Which denotes my final P and Q. Okay, so I have initialized with just minus one, right? This answer 2 denotes my sum of the absolute differences of P and Q with X and Y respectively. Okay. So then I am, as I said, uh, we have concluded that whenever I am doing an adding operation, so it always makes sense to add to just one bit. Okay. So I will add to, so for every bit I am doing what? I am adding something. Okay. So what is that something? So that something is basically like I am adding this 2 ki power I, and then like I am making all the bits after that equal to 0. Okay. So this mask over here, this mask over here. So this mask basically denotes what? Let's say this is my ith bit. Okay. So this mask basically denotes what? All the bits are set for j greater than or equals to I, or it is 0, right? So, so I am taking mask with my number s, right? And then I am adding 2 to the power I, okay? And then I'm checking what? I'm checking if it's bitwise and with y is equals to 0, right? And if the difference is less than all my like my current answer, then I'm updating my answer. Okay. Same I'm doing for y, right? And the other way to do the operation was what? It was to decrease. Okay. So for the first index where my bitwise and is uh, non-zero, I'm doing what? I am again like I am taking this mask. So this mask what it does is, so this mask is just basically all the ones after the so after the ith bit, all the bits are set. So this mask denotes just that, right? And this mask is the same mask as I have used here, but this contains all the zeros from the ith bit only. Okay, so from the ith bit, I am making x equals to 0, and after that, I am adding all the ones. But I'll have to like subtract some ones. What are those ones? So all the ones in which y is also set. So I'm subtracting those from my p. Okay, so yeah, so x has been converted to p. Then I'm checking what is the difference. So if this difference is less than my answer, then I'm updating my answer, and then I'm doing a similar thing for y. Okay, so and then I'm just printing my answer in the end. That is p and q, right? So let's discuss the complexity of this question. So the time complexity is just what? Big of log of n, right? Like n is just the maximum of x and y, or like I can replace this of log n with 30 or something. Okay, so this is quite acceptable. And yeah, space complexity is just big O of 1. So that's all for this question. I hope you liked. I hope you liked the discussion. Yeah, thanks.